Moving on to our next speaker, which is James from SRK. We're giving a talk on advancements in TSF monitoring and surveillance through the adoption of new methods and digital solutions. Thanks, James.
Thanks, Wesley. Morning, everyone. Yeah, as Wesley pointed out, I'm just going to discuss some of the advancements in TSF monitoring and surveillance and some of the adoption of new methods and digital solutions. Again, thank you to Adrian for setting the scene with regards to tailings dams. But just more broadly, technology has always played an important part in the mining sector. We've seen new emergent risks, new rigorous standards, as well as greater expectations. So technology is going to play an important part going forward as well. And that's no different in tailings dams. And this is the area of focus of this presentation today. So what's driven some of the digital transformation in TSF specifically? So infrastructure and technology has been a big driver. We've seen new emergent technologies and obviously the onset of Internet of Things, IoT devices, and that's obviously been driven by connectivity such as 5G and communications and the infrastructure that's now broadly accessible across the country. We've seen new standards and best practices. We highlighted the GISTM, but we're also seeing SANS 10286 being updated, and that hopefully will be out for public consultation this year. And we recently saw the publication of the recent ICOL Bulletin 194. All of these have taken on some aspects of the GISTM terminology as well as some of the principles. Very important documents. Stakeholders have driven a lot of this change and this need for change. Investors, stakeholders and insurers, and obviously the mining communities in which these tailings dams sit. So I'm not going to go into too much detail, but just in terms of the framework, if we look at the GISTM topic 3 and principle 7, specifically states that we need to design and implement operate monitoring systems to manage the risks at all phases of the facility life cycle. So that also includes closure. We need to monitor the apparent structures, the performance of the TSF itself, and obviously try and align with the design assumptions and the design intent of those particular facilities. So where do we start? We talked about knowledge base. Obviously, we want to develop a knowledge base for the particular site as well as the TSF. Now, when we talk about monitoring and instrumentation, it's very easy to implement these things on a newly designed facility. We have the new standards, we have the new guidelines, and we can obviously scale these types of instruments as we go forward. It's a lot more difficult when we're looking at retroactively fitting instrumentation to existing dams, particularly those that are operating. But what do we need to look at? We need to look at the type, the design, and the life cycle stage of the facility as to what the current risks are, and obviously what's happening going forward. We need to try and understand the triggers and the modes of failure, because ultimately need to monitor those as well as manage those risks. So how do we develop a knowledge base for the site? We need to run a series of investigations as well as studies, geophysics, so MASWs and ERI type surveys are now playing an important role, not only on site selection and site investigation, but also, again, iteratively throughout the life cycle of the facility, these types of studies need to be performed. We also do geotechnical investigations, including cone penetration testing, size cone penetrating tests, as well as resistivity seismic cone penetrating tests. So there's a wide range of options there. We obviously do a number of drilling campaigns. Those are supported by laboratory testing, some advanced, some basic. We then go on and do stability analysis and advanced seismic hazard assessment, and then even numerical modeling in the form of deformation modeling. So this knowledge base not only sets the scene and the characteristics of the facility, it also highlights the risks and the ongoing requirements for those facilities, but it also helps us to calibrate our monitoring equipment to that particular site. So if we want to start putting in parameters that are specific to monitoring displacement, then your deformation analysis is going to feed into that calibration. So one area that also gets overlooked when it comes to new monitoring systems is actually how robust the solutions are themselves. So obviously with digital instrumentation these days, they're great until they stop working. So how do we try and avoid that? Well, we're trying to obviously tailor the solution to the technical problems or the metrics that we want to monitor on site. And those are usually aligned with the trigger mechanisms or the modes of failures that we've identified. The implementation needs to be planned, and obviously the appropriate clients, vendors, suppliers, and contractors need to be involved in that process so that ensure that we have a robust system. We also need to look at the quality assurance and quality control of these instruments, not only the manufacturing component, but also right through to installation and calibration. We need to make sure that there's maintenance and critical spares, something again that's largely overlooked, but is critically important. The scalability and the integration of these instruments more broadly into the wider systems needs to be considered. And we also need to look at the scalability. Arjan highlighted these dams can go on for 20, 30, 40 years. And then obviously there's the closure period. These instruments need to be sustainable. They need to be scalable. And that includes the hardware that supports them as well. They need to be resilient, and there also needs to be redundancies. So one system is not going to give you all the answers, but if that system goes down, you need to have a plan in place so that you can continue your performance monitoring, or at least until your system is back up online. Assigning roles and responsibilities again is critical. As EORs or engineer of records, we're not on site every day. We need to make sure that these systems are maintained, managed, and that there's someone responsible either from the operator or on the client side in order to maintain and keep those systems running. There needs to be a monitoring and surveillance plan. We need to understand what's going in, why it's going in, and what that's going to look like going forward. And those need to be integrated into wider plans such as OMS, EPRP, and various other documentation. And then again, we need to train and provide technical support and upskill the people on site to be able to maintain, replace, fix these types of solutions. So what type of solutions do we have? There's quite a few, and there's more coming online every day. We touched on the vibrating wire piezometers. They're very common. Digital weather stations are now pretty common again on most sites, collecting data at a 5-minute frequency. Digital inclinometers such as shape arrays measure subsurface deformation and displacement. We look at fiber optics, is becoming more common and is a real-time data acquisition method. Ground-based radar as well as handheld LiDAR is also becoming very popular. Seismic stations and seismic applications, as Wayne has just highlighted. We're seeing new global navigation satellite systems in place, which is helping us to calibrate INSAR and ground truthing. Tilt and flow meters have a great application, particularly with penstocks, as well as solution trenches, silt traps. We can start to now measure the water that comes into the system and out of the system, which supports water balance interpretation. We touched on just now drones and aerial surveys and the benefits that they perform. Obviously, LiDAR and photogrammetry is very common, but we're now starting to see the implementation of geophysical methods supporting that. INSAR, again, has become very popular and is on a lot of the dams that I manage. Sometimes it's good, sometimes it's bad. I think it's something that's improving. And with the use of GNSS systems, we can certainly start to calibrate them much better. That, coupled with new IoT hardware, such as loggers and gateways, enables us to integrate these networks through cloud storage and edge computing, and obviously start to digitize that data and visualize that on software. So one of the key areas and advancements is the use of digital dashboards. We use them in-house as well as the clients have started to adopt these. Some of the key benefits is that we can start to collect the data, integrate the data, and aggregate the data in automated processes very quickly. We can validate, and we can also put in levels of automation to help with that validation process. We increase the data visibility, transparency, and accessibility, as well as the auditability of that data, not only at an operational level, but up through senior management as well. And that obviously helps to support some of the change management components on site. Using digital dashboards, we're able to introduce new digital rules and protocols. We're able to code, producing automation as well as advanced analytics using statistical analysis. We can do custom digital workflows. That also helps our engineers, but we can also do that for our clients as well. We're starting to see the benefits of real-time analytics. We're able to use these systems to integrate trigger action response plans and integrate a risk management protocol and framework. We can also monitor the instrumentation itself. So not only are we monitoring the performance of the facility over time, but we're also able to monitor the performance of those instruments. Are they still calibrated? Are they drifting? Have they stopped working? What is the problem? And we can usually troubleshoot that remotely as well. And then, of course, communication. Dashboards provide a great source of reporting, notifications, and also enable stakeholder interaction. And again, that's at an operational level all the way through to even ExCo level. So just some applications. This was a paper that was published by a colleague of mine. We've been able to use digital dashboards as well as automated digital processes to start looking at linear regression as well as virtual clustering and VWP pairing. And as I pointed out earlier, the calibration for that model is from the CPTU data. So we're using the site knowledge and the knowledge base in order to inform and infer our calibration process. And what we're able to use now is automated processes to look at the data, process the data, and then do the linear regression pairings in a much quicker time. This obviously can be done in near real time, and that data can then be sent to the client or any other stakeholder that might be interested. We've also had to improve and advance the way that we look at data. We're now getting high frequency big data coming from site. Sometimes this data is in 5-minute intervals, sometimes it's an hour frequency. So there's a lot of data to manage and process. That can take up a lot of time. So through the application and use of Python coding and programming, the integration through API as well as ERP, we're able to store the data, manage it quicker, and structure it quicker. Streamlining the process through some levels of automation. We can introduce data validation into that process, kicking out outliers in the data sets. And then we can apply specialist data analytics to those data sets. What this enables us to do is take a lot of the legwork out of data processing, management, and storage, and actually focus on the engineering component, which I think is where the value comes. We're also, and again, this is where the advancements are also occurring, is that we have had to learn as we go with these new digital systems. And of course, we're now able to support our clients with their own digital systems, supporting their on-site installation, the integration, the quality assurance for that. We're able to integrate new data sets and help develop the associated TARPs. We can advise on the visualization and presentation of the data. We can develop customized dashboards and reports for the clients, again, at different levels of the operation. We can guide the deployment and align with the standards and the frameworks that we discussed earlier. And of course, it also enables us to push research, development, and innovation in this particular space. So what next? So we're seeing new methods. I mean, Wayne outlined passive seismic monitoring, some very exciting prospects there. And I think there's a lot more to come. There's definitely going to be the use of AI, machine learning, and neural networks to help support advanced predictive analytics, perhaps, or at least crunch the data in different ways in quicker processing times to give us more data insights. Yeah, so the opportunities is new data insights. We're starting to see micro trends due to the frequency of the instrumentation that we're using. We're also able to see other parameters that come off as an offshoot of those particular monitoring solutions. And that's obviously opening up doors to us, better identifying the risk, change in the performance of the facility, and also it helps to increase our knowledge base over time and iteratively throughout the life cycle of the TSF. But with that comes challenges. We're seeing big data. We're having to now look at how we store that data, have access to that data, as well as making it available for any reasons in the future. Data security, everything now is being stored in the cloud. That concerns some clients, and obviously losing that data or having it corrupted would cause big problems. So that's an area that we need to look at. Governance and over-reliance. These are great. It's great to have all the instrumentation, but are we going to use it blindly? Are we going to over-rely on it? And that's something we need to be careful with. And of course, from a governance perspective, when we talk to AI and the ethical aspects of it, we need to make sure that we manage that carefully. So just in summary, digital transformation and adoption of TSF monitoring is still evolving, and it's still got a long way to go, I think. New technologies and their applications are becoming apparent. We're seeing older methodologies being applied to the tailing space. We're seeing better integration of the data, management of that data, as well as access to the data. The data frequency and visualization provides clear benefits. We're able to present the same data to all of the stakeholders so that everyone's looking apples with apples. We're able to also cater for the different types of data that people want to see at different levels. And again, that's helping us to better drive performance monitoring, identify these changes, the potential risks, and ultimately make better informed decisions proactively instead of reactively. And just some final thoughts. Leveraging current and new technologies such as AI and machine learning and collaboration with industry and innovators is going to play a strategic role going forward. Digital adoption is giving us new methods and solutions to tackle the problems that we have on tailings facilities. And this should improve performance monitoring and TSF's performance monitoring in the future and hopefully reduce risks. And obviously I've got colleagues in the room, so I've added this extra one. Technology never replaces good engineering judgment and robust interpretation. Thank you.
Awesome. Thanks, James. I think one quick question. Again, James is active in the tailings space and is a specialist in this. So specifically for the geophysicists, do you have any questions? Like one quick question for James, right?
Thanks, James. Just in terms of the, I suppose, hazards posed by TSFs, I haven't heard too much about, let's say, pollution of groundwater, the impact on community, and dust. Are these also factors that are monitored?
They are. It's an area that's largely monitored by the environmental teams or social teams. They can either be mine-based or external consultants. But what's nice about some of these monitoring solutions, they only need to go 200, 300 meters beyond the boundary of the facility, and we can start to integrate this data as well. So we can bring in environmental data, dust monitoring data, water quality data. If we can put a device that sends that data to the cloud, we can fully integrate it into a wider system. And I think that's a natural next step.
Awesome. Thanks. I think we'll end it there and we'll catch up later. Thanks, James.